Good afternoon, dear students. Today we have lecture number 10 and today's class will be dedicated to the topic RLC Circuit Analysis. So, dear students, till now we have discussed in detail the source-free RL and RC circuit, and we have also seen in detail the forced RL and RC circuit where we have either current source or voltage source present in the circuit. Then further, through a number of numerical examples, we have developed concepts related to the analysis of circuits um, based on your RL and RC. So today we are moving one step further, that is RLC. Now in our circuit, both L and C will be present. And let me tell you, dear students, when both inductor and capacitor comes in a circuit, then some oscillations will be generated. So in that way, let me tell you that these RLC circuits, they are very, very important because practically in circuits, we have all the three components effect present. You must have heard of the term resonance in your earlier classes, in your junior classes. So this term resonance has come only through these RLC circuit. If you study these RLC circuit in detail, you will come to know about the term resonance. And in resonance, you all have seen that we have a peak response at resonant frequency, and it also behaves like a filter. Okay, so this was just to give you a brief idea about where you can correlate your RLC circuit with the content that you have studied earlier. So these are the books that we are following for the content that we are discussing in this class. So we are going to start our today's class with source-free parallel RLC circuit. So students, you look at the left hand side of your slide that we have R, we have L, and we have C present in the circuit, and all these three circuit components, they are in parallel. Further, we have source-free RLC parallel circuits. So source-free means there is no voltage source or there is no current source present in this RLC circuit. So as we have discussed earlier in RL and RC circuit, in case of source-free circuit, we will have the natural response present for that circuit. So the concepts that we have developed for RL and RC, same kind of concepts will be utilized here for RLC circuit as well. Though a bit form will change in the form of the equation of RLC circuit and the methodology to find out the value of voltage and current in RLC circuit. So let us see that. So students, in this circuit, we have to determine the voltage. And you can see that since it is a parallel RLC circuit, we can apply either KCL or nodal analysis for the solution of this circuit. So we all know that this V will be a function of time. So that's why this V is nothing but Vt. So the same kind of notations we are using as we have done in our previous classes. So if we apply KCL to this node, we know that according to KCL, the sum of currents at a particular node is equal to 0. So if we apply KCL at the node which is designated as V, in that case, the current which is going out through this branch, it will be V by R. The current which will be going out through this branch, that will be I is equal to C dV by dt, that we have already seen in our capacitor concept building slides. Then this is inductor. So in an inductor, the governing equation is V equal to L di by dt. And now we need current. So that's why this equation has been shown as 1 by L integral V dt. I hope you could understand that. In case of inductor, the equation is E is equal to L di by dt. So if we want to find out I out of this equation, we'll have to take this dt towards left hand side. It will become e dt or v dt, this one. Then L will be 1 by L, and since we want to obtain I, so we need to integrate. So if we integrate, this is what we get, 1 by L integral v dt. Okay, and dear students, we have talked about three terms. So we look at one more term which is present in this equation. This we have not anticipated, and I think by looking at this term, you are able to judge that this is the value of current at T0. T0 means initial condition. We know that the current through inductor, it cannot change instantaneously. It means the current through inductor that was present before t equal to 0, that will also remain here. So this IT0 is nothing but the current present initially across this inductor. This E equal to LdI by dt equation, it does not give us the initial value of current. So this current we have to take into account since we are considering KCL. So that's why this term has been included here, which indicates the initial condition. Now next question is, why are we having minus sign? This we also have seen in detail, that the current which will be there as initial condition in inductor, that will be opposing the things. Okay, or whenever you apply some voltage or some active component across this inductor, it will oppose the building of current. So that's why this initial current has been shown with negative direction. Okay, so that way this is the equation for KCL in this parallel RLC circuit, and the sum of all currents is 0. That's why it has been equated to 0. So students, now we need to solve this equation in order to find out the value of Vt. So in order to solve this equation, we need to differentiate this equation once. So if we differentiate, then what will happen? This integral will go away. Wherever we have single differentiation, we will get second order differential, and this V will also be differentiated. So you see here, this C dV by dt, it becomes C d2V by dt square. Then this 1 by R into V will become 1 by R into dV by dt. This integral equation, integral sign will go because of differentiation, and we have 1 by L into V. And we know that the initial condition is a constant. It's not dependent on time. Once we have fixed the time, IT naught means the value of current at a fixed particular time. That means it will be a constant value. And if you differentiate constant, you get 0. So this is the governing equation of a parallel RLC circuit, which is source free. So in a way you can say that this equation is the desired natural response of this RLC source free parallel circuit. And from this equation, now we need to determine the value of Vt. So we need the solution of this equation. So dear students, now we have to understand how to come at the solution of this equation. If you remember, in RL and RC circuits also, we had got differential equation and then we had solved that equation, but that was first order linear homogeneous equation. Here we have second order linear homogeneous differential equation. Okay, so we have d2V by dt square. That's why it is second order homogeneous linear differential equation. So now we come to the solution of the equation that we have developed in the previous slide. This is the equation which I have reproduced here for your ready reference. So students, the way we had got the response, natural response in case of RC and RL circuit, we assume here first that same kind of response we will obtain in case of RLC circuit as well. But there is a change here. We are assuming a generalized solution in a way that we have taken Vt is equal to A is a constant, then e raised to power s into t. For the time being, you consider this s as some hypothetical parameter. Okay, so we can very easily assume this, the value of s would be negative, positive. Let's see what comes when we solve this equation. Okay, so presently we are assuming that the solution of this equation is v equal to a e raised to power st. So it is reasonable assumption. So that's why we substitute this v equal to a e raised to power st in this equation that we have developed in the previous slide. So after substitution, this is what we get. We get a e raised to power st common, then c s square plus 1 by r into s plus 1 by l. Now we have to obtain solution of this. So here we have two terms. One is a e raised to power st and second is the term within brackets here. Okay. So if we want answer 0, that means either this should be 0 or this second term should be 0. But we cannot have the first term equal to 0, because if we make first term as 0, then our assumption means the voltage itself will become 0. This will become 0, which is not possible. If we make it 0, our entire solution will become 0 then. So the non-trivial response, or the other way is, then it means it should be 0. Only then we will have this total multiplied equal to 0. So what we do, we equate the term which are there in the bracket equal to 0, and we call this term as characteristic or auxiliary equation. This is very, very important point. Students, you keep this equation in your mind. This equation will be very frequently used in the subsequent units that we will be discussing in the coming chapters or in the coming classes. Okay, so very commonly you are going to face this characteristic equation or auxiliary equation. Okay, fine. So wherever you will come across second order linear differential equation, homogeneous linear differential equation, you will come across such kind of thing. And let me tell you that just to satisfy your curiosity, that this S is also called as complex frequency. Right now you can simply consider it as a complex frequency without having further query in your mind. Okay, so now this is a quadratic equation. You can very clearly see to it. So what we have done, we have basically rewritten this equation as s square plus 1 by RC. What we do, we divide both sides by C. So we come to this one, 1 by RC into S plus 1 by LC. So now this is clearly observable as quadratic equation. And we know the solutions of quadratic equation, that if we have a quadratic equation, then the solution is minus b plus minus under the root b square minus 4ac divided by 2a. This is very common solution that you have already studied in your school level, in fact. Okay, so same kind of thing we apply here. So since it is a quadratic equation, second order equation is there, there will be two solutions. So the two solutions are S1 and S2. And if you substitute these things in this equation, you get two solutions, that is S is equal to minus 1 upon 2 RC plus under the root this one, and another is minus. Okay, so this is the solution of quadratic equation that we come across. Okay, students. So after observing in the previous slide about the solution of quadratic equation and looking at the two solutions or two roots of that quadratic equation more precisely, we have obtained these roots. Now we move further. Since there are two roots of the equation or two solutions of those equations, that equation, and that equation is V is equal to e raised power st. So if we let us assume that these are the two solutions. So obviously the final solution will be summation of those two solutions, as I just talked about linearity. Okay, so the general form of natural response will be the sum of these two responses. So we can easily put these two roots in the equation, and the final response can be seen as the you can say superposition of those two solutions. Here we will redesignate few quantities. So what we have done, we have substituted 1 by 2 RC equals to alpha. Okay. And then we have substituted 1 by under root LC equals to omega naught. So students, I talked about in the very first slide of today's class about the resonant frequency. So we have brought in the concept of resonant frequency in our equation here. So this omega naught is the resonant frequency, and alpha is called as exponential damping coefficient. Right now you need not worry about the explanation of these terms. You can simply memorize the nomenclature of these terms. So their explanation will come in the time to come. Okay, so if you substitute the value of alpha and omega naught in the two roots of these quadratic equation, these roots become like this: S1 is equal to minus alpha plus minus under the root alpha square minus omega naught square. Okay, so now if you again recall the concepts of quadratic equation, you know that the two roots that we got from quadratic equation, those two roots could be the real numbers, those two roots could be imaginary, those two roots could be equal. Okay, so if the two roots are real number and different, that condition will come when this under the root equation terms are defined like this: alpha is greater than omega naught, means this under the root term is positive. So if we have this term as positive, we will have the two roots as real number, and in that case alpha is greater than omega naught. The second situation comes when alpha is less than omega naught. So if we have alpha less than omega naught, we'll get under the root minus. So if we have minus sign under the root, then we have imaginary roots present. And third condition is when alpha is equal to omega naught. In that case, this term will go away. Okay, and this plus minus thing will also no longer be significant, and we will be left with two roots, and those two roots will be equal. Okay, so third condition will come: alpha equal to omega naught. This is mathematical representation of the roots of the quadratic equation. Now we try to interpret these three kind of solutions in terms of electric circuits. So in case we have positive term inside the under root, we will call that condition as overdamped. If we have imaginary kind of roots present, we will call that condition as underdamped. And if we have equal roots where alpha is equal to omega naught, we will call that circuit as critically damped. So dear students, you please remember these three terms: overdamped, critically damped, and underdamped. Okay, I hope you have studied about resonant frequency, you have studied something about oscillations and your filters. So wherever we have oscillations means some sinusoidal kind of response is there. Damping means suppressed oscillations, or you can say that the amplitude of oscillation is decreasing. Okay, so you can correlate these overdamped, critically damped, underdamped thing with those oscillation thing that we will discuss in detail later on. Another term that we need to know about is damping ratio. So these two parameters, one is alpha and another is omega naught. If you take their ratio, that is ratio of alpha to omega naught, is known as damping ratio. And let me tell you, dear students, the control system engineers You will have a subject control system in your future semesters. You will very frequently come across this term damping ratio, over damped, critically damped, under damped in the control system subject. Okay, and this damping ratio of alpha by omega naught, it is also designated as zeta. This is the sign of zeta. So presently you need not worry about much about these parameters. You simply remember their names and the terminology associated with it. Okay, now let us move forward. So dear students, after looking into the terminology of this overdamped, critically damped and underdamped, we take the case of overdamped circuit condition first, where alpha is greater than omega naught in the next slide. So you see here, we are considering a numerical example which is having overdamped response. So here we have taken alpha is equal to 3.5. We have taken omega naught is equal to under the root 6. In fact, the value of alpha and omega naught, it has come from your circuit component values, that is R, L and C. Okay, so if we go to previous slide, you just see what is alpha. Alpha is equal to 1 by 2 RC. Omega naught is 1 by under root LC. So students, the value of alpha and omega naught will be decided by the circuit components. Okay. So the way your value of time constant tau was defined by circuit components, in the same way, the value of alpha and omega naught is also defined that way. So once we have this circuit, the value of alpha and omega naught is available with us. So by using the value of alpha and omega naught, if you look at this equation, you will be able to find out the two roots, that is S1 and S2. So value of S1 will come out to be -1 and S2 will come out to be -6. So I'll request all the students to solve this value of S1 and S2 by putting in the equation and try to cross verify whether this is correct or not. So as we have seen in the previous slide, the total natural response will be equal to the two roots or two solutions that we have obtained, summation of those responses. So if we substitute the value of S1 and S2 in that, we get this equation. So if you remember, in RL circuit and in RC circuit, we represented its natural response as A e raised power minus T upon tau. Whereas in RLC circuit, we are taking natural response as A e raised power ST. More precisely, you take it as A1 e raised power S1t plus A2 e raised power S2t. You can take this equation as natural response for source free parallel RLC circuit. So we substitute S1, S2, we get this equation. Now our objective is to find out the answer to this equation or solve this equation. This equation can be solved by determining the value of A1 and A2. So our next job is to find out the value of A1 and A2. And the way we obtained the value of A in case of RC and RL circuit, in the same way we will try to find out the value of A1 and A2, and we will require initial conditions for that. And dear students, since we have two constants here to be determined, that is A1 and A2, so we need two initial conditions. And obviously the two initial conditions can be very easily obtained. Obviously we have inductor, we have capacitor present. So one initial condition will be coming from, you can say, inductor, another from capacitor. But so it is very easy to obtain two initial conditions here. So let us see how will we apply those initial conditions. If you look at the circuit carefully, the two initial conditions are already told to you. Okay. So your V0 is 0. This is the V voltage at this node. So the voltage is 0 at t equal to 0. This is one initial condition. Second initial condition is I0 is equal to 10 ampere. This I is this one, that is current across inductor. This is IC, this is R, IR. And we are given the initial current for inductor, that is equal to 10 ampere. So now let us see. First, we apply one initial condition to this equation. So we put t equal to 0, we get V0. This is V0. Okay. Then this V0 is equal to 0. So if you put 0 here, then you get what? At time t equal to 0, e raised to power minus t will become 1, e raised to power minus 6t will become 1, and we get a1 plus a2 equal to 0. Now we have two variables and only one equation. So we need one more equation to find out the value of a1 and a2. So what we will do now, we will differentiate this equation. This step we did not have in RC and RL. This is the new step that we will carry out in this RLC circuit. We will differentiate our general form of natural response. Once we do that, we get dV by dt. Then a1 e raised to power minus t differentiation, we get minus a1 e raised to power minus t. Then the second term differentiated give us this one. And it is quite evident and very simple thing. You can easily make out that how have we arrived at this thing. Now, since we need to apply second initial condition, we will apply initial condition to the derivative part. So here we have written dV by dt at t equal to 0. If you put t equal to 0 here, you get minus a1 minus 6a2. So in order to find out the value of a1 and a2, we need the value of dV by dt at t equal to 0. So we will have to see how do we come at this particular value. If you look at this thing very carefully, we know that dV by dt comes in capacitor. The current through capacitor is given as IC is equal to C dV by dt. So if we are able to find out the initial current across the capacitor, we'll be able to find out answer to this. Let us now see in the next slide, how do we arrive at that? So we have dV by dt equal to t equal to 0, and this is equal to IC0 by C. The equation is IC is equal to C dV by dt. If we want to find out dV by dt at t equal to 0, C will come towards right hand side, and we get dV by dt equal to IC0 by C. Okay. So now we need to find out IC. We do not know its value. We know the value of I0, that is 10 ampere, means this value we know, but we do not know the value of IC. But if you look at this particular node carefully, then apply KCL. So this capacitor current, it is shown going out, and this small I and IR, these are the incoming currents. So IC will be equal to I0. I0 means this current through inductor, and the second current is IR0. Okay. And students, we know that across resistance, there is no storage of any current or voltage. So this IR0 is 0. Okay. But this I0 is not 0. This is given as 10 ampere. So this is 10. Capacitor value is 1 by 42. And this dV by dt at t equal to 0 comes out to be 420 volt per second. And why it is volt per second? dV is volt and dt is your second. So we get second equation, that is 420 equal to minus a1 minus 6a2. Our first equation was 0 is equal to a1 plus a2. And from these two equations, we can calculate the value of a1 and a2. So a1 and a2 comes out to be 84 and minus 84. And if you substitute that, you get this form of natural response for the source-free parallel RLC circuit. So students, whatever analysis we have seen in RL and RC circuit, same thing follows here, except one new thing. And that new thing is that we need two initial conditions. We have second order equation. We need to find out two constants, and then we get the answer. So very simple. If you proceed systematically, there will be no problem in finding out solution to even RLC circuit. So dear students, in the last slide, we had talked about the overdamped response. Now we talk about underdamped response. And students, as I told you, there are three conditions. One is overdamped condition, second is underdamped condition, and third is critically damped condition. So we have discussed overdamped condition. Now we will discuss underdamped condition, and third condition will be discussed later on. Students, in RLC circuit, your first job while analyzing those circuit will be to find out whether the circuit under consideration is overdamped, underdamped, or critically damped. After determining this thing, then you will come to the equation of that. In case of overdamped circuit, the equation we have already seen. Its solution was V is equal to A1 e raised to power S1t plus A2 e raised to power S2t. And in case of underdamped response, the equation will be something different, and we will see to that equation. So now let us see. This is the same circuit that we have previously seen. This is the equation that we had previously obtained. These are the two roots. The only condition for underdamped is this alpha square minus omega square. This thing is less than 0. Okay, since this is less than 0, so we will be having negative thing inside. And dear students, you all know that what is the meaning of under the root minus 1? Under the root minus 1 is nothing but iota. And in case of circuit theory, we do not represent iota by I. We do not do that. आपने मैथमेटिक्स के अंदर iota को I से represent किया होगा in case of complex number. But in case of circuit theory, we represent your iota or complex number by J. And the answer for that is because in circuit theory, we represent I, or we represent current through I. So that's why we do not represent iota by I, we represent iota by J. So if we consider under the root omega square minus alpha square, which is reverse of this, is equal to omega d, then this will come out to be, these two solutions will be minus alpha plus minus, okay, J is your complex iota, omega d. So these are the two roots of that equation, minus alpha plus minus J omega d. And omega d is nothing but this under the root, omega naught square minus alpha square. So if you substitute this minus alpha plus minus J omega t in this equation, this is what you get. E raised by minus alpha t will come out to be common. Inside you will get A1 e raised by J omega d dt. Then A2 e raised by minus J omega dt. Okay. D is the subscript. Okay. So this is the equation that we get. Now, I hope you remember this relationship that if we have e raised to power J theta, e raised power J theta can be written as cos theta plus J sin theta. I hope you have studied this thing in your +1 and +2 in mathematics. J sin theta. Okay. So same relationship we apply here also. We have here e raised power J omega dt. This will come out to be cos omega dt plus J sin omega dt. And here you will have, this is e raised power plus minus J theta. So if you have plus, you will get plus here. If you have minus J theta, there will be a minus sign. So corresponding to this minus J omega dt, you will get cos theta or cos J omega dt minus sin J omega dt. Okay. So if you substitute those and you club cos term and sin term, you will come to this equation. So under the cos, you will have A1 plus A2, and under the sin term, you will have A1 minus A2, and this J is the imaginary term. Okay. So we again represent in a new way. A1 and A2 we represent with B1, and A1 minus A2 we represent with B2. Okay. And this is what we get here. So let us move forward. So this is the circuit that we studied for the case of overdamped also. Now we have converted the same circuit to underdamped. Okay, and for that we need to change the value of alpha and omega naught, and in order to change the value of alpha and omega naught, we need to change the value of the circuit component. And here we have changed the value of R from 6 ohm to 10.5 ohm. So if you do that, your alpha will come out to be 2 and your omega naught will come out to be under the root 6. Okay, and here you can easily see that your omega naught term is greater than your alpha term. Okay, so that's why we get underdamped response, and from the value of alpha and omega naught we calculate omega d. Omega d comes out to be under the root 2 radian per second. Okay, and as we had seen in the previous slide, that this was the governing equation of natural response for underdamped response. Okay, so here we come to this one. So what we have done, we have substituted the value of omega d as under the root 2 in this equation, and this is the equation for this circuit. Otherwise, for the case of your underdamped response, this is the equation that you have to memorize, where B1 is A1 plus A2 and your B2 is J times A1 minus A2. Okay, so this equation we have come to, and now our job is to find out the value of B1 and B2. So again, two constants, we need two initial conditions. So those initial conditions will be arrived at in the same fashion. That is, your B1 will be obtained by, you can say, applying these initial conditions. Let us see those. So now we determine B1 and B2. So students, first we know that V0 is 0. So this is the equation. So here if you put V0 is 0, your sine 0 will be 0, you'll be left, cos 0 will be 1, you'll be left with only B1 multiplied with this. So obviously B1 has to be 0 for this Vt equal to 0. So your B1 comes 0. So if you, in that case, if you remove B1, then the equation becomes Vt equal to B2 into e raised to minus 2t sine under the root 2t, because our B1 has come out to be 0. So we are left with this. Now, in order to apply second initial condition, we need to take its derivative. So we take dv by dt and differentiate this equation. So if we differentiate, you already know how to differentiate if there are two time terms in multiplication. First, we will consider one term, differentiate it, and then assuming second term as constant and then differentiating the first term. So you all know the rules of differentiating. It has been differentiated. So now we need to apply initial condition to the derivative part. So that is dv by dt at t equal to 0. So that we have already seen that dv by dt is equal to IC0 by C. Okay, and that value is 420. Fine. So we have got dv by dt equal to 420. If you substitute this thing here, you'll be able to find out the value of B2, and that B2 value is substituted in this equation. Okay, and this is the final answer to this question. Okay, dear students, so today we have discussed source free parallel RLC circuit, and we have seen two conditions. One is your overdamped conditions and second is your underdamped condition. In the next class, we will talk about further things, that is if we have force response in RLC circuit, and third is your critically damped conditions. So I hope all of you have understood what was told in today's class, and I hope you will read further related to RLC circuit. So I stop here. We will continue in the next class. Thank you.